Thank you for the introduction. Hello everyone, my name is Xiaojie Guo, and today I'm going to introduce half-tree halving the cost of tree expansion in COT and DPF. This is my joint work with Kang Yang, Xiao Wang, Wenhao Zhang, Xiang Xie, Jiang Zhang, and Li Liu. So let's begin with our motivation of this paper. And as we will see, GGM tree has been used to generate correlated randomness with sublinear communication. However, GGM tree has no algebraic structure, so that we have no opportunity to optimize the efficiency of the previous protocols. Here, GGM tree is stretched from a root K using length doubling PRG. Here, we use G0 and G1 for its two halves. And the alpha sleeve is defined to be the recursive PRG evaluation according to the bit decomposition of alpha. And there are many useful correlated randomness from GGM tree, including correlated observers transfer subfield vector OLE, distributed point function, and distributed comparison function. Here we use COT, SVLE, DPF, and DCF for short. And there has been many MPC applications using this correlated randomness. And in this work, we propose more efficient protocols for the four kinds of correlated randomness. And the core idea is that we can introduce actual correlation to the GGM tree so that some of its nodes are summed to a global offset. And we will see how this global offset can be used to optimize the efficiency. And in this work, we consider the semi-honest UC security in the random permutation model. And the random permutation model is usually implemented using fixed key AES in practice. And we know that the malicious security can also be obtained by using corresponding consistency check. And here we summarize our improvements on computation, communication, and round complexity. We know that for COT and SVLE, we only measure the computation in the number of AES calls for tree expansion and do not consider the cost of LLPN encoding. And according to the previous works, the computation for tree expansion can be significant. And in a concurrent work by Boyle et al., the authors also consider how to optimize the computation using modified GGM tree. However, their work require random oracle model or some ad hoc conjecture, and they do not consider how to improve the communication. In contrast, our work works in the random permutation model for both COT and SVLE, and with both improvements in computation and communication. Okay, let's begin with the brief recall of how can we construct COT or SVLE. Here, SVLE is parameterized by a field F and its extension field K, and the COT is a special case of SVLE. In an SVLE correlation, the sender has a global key delta and an output vector V, while the receiver has two output vectors U and W. And in a previous blueprint of SVLE, one can obtain SVLE from single-point SVLE plus LPN encoding. Here, the single-point SVLE stands for a spatial SVLE where the vector U has exactly one non-zero entry. And for example, we can consider regular LPN noise with dual LPN assumption. And here, the two parties set up many single-point SVLE correlations and combine them into longer vectors. Then they can use local LPN encoding matrix to turn these three vectors into the output vectors V, U, and W. And these three vectors correspond to the target SVLE correlation with respect to the global key delta. And the key point is that how can we set up a single point COT or SVLE efficiently? In the previous work, the sender has to set up a GGM tree and use its leaf nodes as its output vectors V. And the receiver picks a random point alpha and uses its negative bit decomposition to select the left or the right sum for each level of the sender's GGM tree. This allows the receiver to level by level recover the all leaf nodes except the alphas 1. And to patch the punctured points, in the single point COT, the sender needs to send one additional message. And in the single-point SVLE, the two parties require one pseudo-random SVLE, which picks the global key delta for the sender, and the sender still needs to send one additional message. And in this work, we can replace the GGM tree with the correlated GGM tree. Here, the correlated GGM tree has the nice property that all the sum level nodes are summed to a global offset delta. And to maintain this property, we can define for each node and its left child node as h of x, and the right child to be x minus h of x. Here, h stands for hash function, and we can use the construction from a GKWY. In this construction, pi is modeled as random permutation, and the sigma is modeled as the efficiently computable linear isomorphism. And let's see how we can construct single-point CLT from CGM tree. Here, the sender constructs a CGM tree with the global offset delta, and the receiver interacts with the sender using delta CLT instead of the standard OT in the previous works. Here, the delta CLT picks the random point alpha for the receiver, and the receiver can recover all leaf nodes except the alphas 1 using the same computation as the previous works. However, in the delta CLT, we can use the same global key as the global offset of the CGM tree. And this has the nice property that in the delta CLT, we can use one preprocessed random CLT. And then in this way, the sender only sends lambda bits messages to the receiver, and the receiver can use this message to recover the left or the right sum of the sender's GGM tree for each level. And in contrast, in the previous work, even in the CLT hybrid model, the sender needs to send 2 lambda bits. And that's why we can save the communication for the previous single-point CLT. And let's have a look on the CGM tree-based single-point CLT. The semi-honest security is straightforward for the corrupted sender, but however, there is a subtle issue if the receiver is corrupted. The reason is that the environment can lens the global offset delta from the only sender's output. And in the real world, there is a consistency with respect to this delta. And however, in the ideal world, this consistency does not hold with overwhelming property due to the random transcript simulated by the simulator. However, we notice that the hash function is constructed from the random permutation, so the environment has to query the random permutation or its inverse to detect this inconsistency. So we can address this issue by relaxing the single-point CLT functionality to allow the global query on delta. Then the simulator can extract every possible delta from the queries to the random permutation or its inverse, and interact with the ideal functionality to guess each extracted delta. Finally, the simulator can program the random permutation or its inverse to be consistent with the ideal world delta. And our single-point CLT from CGM tree can also be extended to realize a single-point SVLE if we assume the two parties have access to one preprocessed random SVLE. Here, this random SVLE picks the global key delta and the global offset k beta for the sender. And the sender constructs a CGM tree from the k beta. Using the k beta for the global offset. And the two parties interact using k beta SVLE. Here, the k beta SVLE still selects the random alpha for the receiver, and the receiver can recover all leaf nodes except the alphas 1. And in the construction of this k beta SVLE, we require one spatial SVLE with the global key k beta. And this spatial SVLE is to ensure that the choice bit Ri or alpha I is a uniform bit. And using k beta SVLE, the sender only sends one additional message to the receiver. And the receiver can use this message to recover the left or the right sum of the sender's CGM tree for each level. And of course, we also use we also consider how to use the previous blueprint to construct single point SVOE. And this blueprint requires pseudo-random of path nodes and the pseudo-random puncture leaf. Unfortunately, this pseudo-randomness does not hold in our CGM tree. But fortunately, we can modify our CGM tree to ensure this property. And we call a modified CGM tree pseudo-random CGM tree, or PCGM tree for short. In this PCGM tree, the first n-1 levels are the same as the CGM tree, but we break the last level correlation using additional hash evaluation. Concretely, for a node X on the n-1 level, we define its left child to be h of x and the right child to be h of xo1. And in this conjunction, we have 3 of path nodes x1 to x3 and 1 puncture leaf x3 prime. It's easy to see that x2, x3, and x3 prime has the form of circular correlation robustness. And this CCR with respect to delta works through as that. Here, the global offset in the PCGM tree is delta, but this delta is not the global key of the single point SVOE, so that we can make a reduction to the CCR gain and to ensure the pseudo-randomness of these nodes. Now we go to the DPF and its protocol. Here the point function f of alpha beta is evaluated to beta if the input x is equals to alpha. And the distributed point function is a function secret sharing of f alpha beta with the following 2 phases. In the first phases, there is a trusted dealer or a secure protocol distributing DPF keys to the 2 parties. And in the second phase, each party uses its DPF keys to perform local full domain evaluation to obtain its additive secret share of a vector R. And by summing the sum of the 2 additive shares gives a vector R, and this vector R is the full domain evaluation of the point function f alpha beta. In the previous work, the key generation protocol of DPF is based on secure 2-party computation and the black box evaluation technique. For example, the DPF key of a party PB consists of an additive share of the root and n+1 public correction word. And a node of a party's tree consists of lambda bits, and the upper lambda -1 bits are used for PRG evaluation. And using the GGM tree algorithm, each party can define a GGM tree and use a correction to correct its GGM tree. Here we use red and blue color to highlight the 2 kinds of correction. And the correction ensures that by summing the 2 parties' corrected GGM trees, the summed tree has pseudo-random nodes along the path alpha, and these nodes are pseudo-random conditioned on the non-zero LSB. And the output node is also corrected to beta using the blue correction. And this correction ensures that for each level, the correction word should depend on some shared bits on the alpha. And this requires 2-round OT-based 2PC in the distributed key generation protocol. And in our protocol, we observe that we can have a simpler correction with each CWI for the first n-1 levels. Here we color the correction in green. And our tree expansion follows from the CGGM or the PCGM tree expansion for the first n-1 levels. And the correction with respect to this tree expansion ensures that For the first n-1 levels, the sum of the two parties' tree shares equals a global offset delta. And this delta has a non-zero LSB. And otherwise, we have the same construction here, just like the red and blue correction as the previous works. And this property has a benefit for our each CW for each of the first n-1 levels, as that the first part of each CWI can be locally shared by the two parties using the black box evaluation technique, and the second part of each CWI can be securely computed in parallel for all of the first n-1 levels. As a result, each CWI can be securely computed in amortized one round and has CCR form to ensure its pseudo randomness. And now let's go to the distributed comparison function, which is closely related to the distributed point function. Here, a comparison function f alpha beta is also evaluated to beta if the input x is less than alpha. And distributed comparison function is a function secret sharing of f alpha beta. And we can interpret the comparison function as the sum of a spatial point function and a prefix function. Here, the prefix function depends on the longest common prefix between alpha and x. And in the previous construction, this prefix function is implicitly computed in the DPF part for the spatial point function. And let's briefly recall how the previous construction works. Here, the DCF key of each party consists of the DPF key with n additional correction word VCW1 to VCWN. And in the tree expansion, each node spawns 2 additional child nodes using length quadrupling PRG. And these additional DCF nodes are also corrected to ensure that by summing these additional nodes along the path alpha and the output of the DCF part, this gives a evaluation result of the comparison function f alpha beta. And to ensure this correction works, each VCW should also depend on some bit of the alpha, and this bit is secretly shared in the distributed protocols. And that is, we need 2 round OT-based 2PC in the distributed key generation protocols for each VCW. And in our work, we have 2 optimizations for DCF. The first one is that we can use our optimized DPF and its protocol for the DPF part. And our second optimization is that we can have a simpler correction for the DCF part. Here we give an example of our second optimization. We observe that 1 additional node is sufficient for each node, and there is no need to introduce masks in the shared tree of the 2 parties. And in this way, if we use this second optimization with the first one, we can also construct each VCW using the delta-related CCR. And in this way, some part of the VCW can be locally shared using the black box evaluation technique of the DS17. And the other part of the VCW can be securely computed in parallel, so that we can also save the round complexity and the communication of the previous DCF construction. And that's all of my report. Thank you.
Thank you very much. Questions? Okay, so you mentioned at the beginning that you need a preprocessed random COT. How many do you need? So,
we only need a sublinear number of the the best COT, just like the silent preprocessing by the previous works.
And then to obtain you obtain how many single points?
We need random COT to obtain single point COT, and the number of the random COT is sublinear in the length of our final single point COT.
Okay.
Yeah.
Thank you. More questions? Okay, so let's thank you, the speaker, again.